Okay, welcome to part 2. So here we are talking about the Challenger explosion again. Couple important pieces of information here. They estimated the probability that one particular O-ring joint would function properly was 0.977. The other really important piece of information is the fact that we've set assuming that they succeed or fail independently. So we're going to find the probability the shuttle would launch safely under similar conditions. Now, there are 6, and they all had to function properly. So the probability that it would launch safely is going to be the probability that they are all going to be okay. So it's going to be the probability that ring number 1 is okay, times the probability that number 2 is okay, times the probability that number 3 is okay, etc. And there's going to be 6 of these. Now, we said that it's going to be independent, so it doesn't change. If I know that ring number 1 failed or succeeded, it's not going to change the probability for 2 or for 3 or for 4, etc. So that means each of these probabilities is going to be 0.977. So it's going to be 0.977 times 0.977 times 0.977, and you're going to do this 6 times. Now, fortunately, you guys have all taken algebra, so you know that we have a mathematical shortcut. So I don't have to actually write this 6 times. We're going to say that this is equal to 0.977 to the 6th power. And if you stick that in a calculator, it turns out it's about 87% that it would launch safely. So there's a 13% chance that you are going to die. I think you guys would agree that that is too large a chance. So you will probably be happy to know that as a result of the statistical analysis that happened afterwards, they have made important safety changes. For instance, now they believe in redundancy. It's not that they all have to work correctly. If one or more of them do fail, we have fail-safes and backups just in case something does happen. All right. I'm going to do one more example with you guys, and then the one on the next page I'm going to actually ask you guys to do on your own. So here we go. We're looking at batteries in your calculator, and we're going to say you use 4 batteries in your calculator. The probability of an individual battery being defective is 0.1. So we're making a really big assumption here, and that is that these batteries are going to be independent of each other. Now, in real life, that may or may not be true. I mean, you might have bought all your batteries at the same time in the same batch, so they could have all come from the same bad batch, for instance. But we're going to go ahead and make that assumption, that these batteries are either going to be defective or not independently. This is a good time to look up at the whiteboard. If all has gone well, you should see a nice tree up on there that represents whether or not your batteries are defective. So, I mean, here's one real quick. So here is the first battery is defective or not. The second one is or not. The one on the whiteboard actually probably says good or bad, whether it's good, whether it's bad. So refer to the one that's up on the whiteboard so you don't have to keep on rewinding and looking back at this one. So we're going to be looking at these 4 batteries and whether or not they're defective or not defective. And again, it's probably going to be easier. Just look at the one on the whiteboard right now. It should show you a nice tree, and it shows you good or bad, good or bad, good or bad. So the probability that all 4 of these are defective, well, we're assuming they're independent. So that would mean that the first one's defective, times the second one's defective, times the third one's defective, and the fourth one's defective. And that probability is not going to change. So it's going to be 0.1 times 0.1 times 0.1 times 0.1. Or as we do in math, we can do 0.1 to the 4th power, which you guys should be able to do without looking at a calculator. It is going to be 1/10,000th. So probably that all 4 are defective. Now, part B is what is the probability that none are defective. So go ahead and look up at the board, and you will notice that there are 15 branches that have at least 1 defective. So this is when we start looking at, oh, maybe this is going to somewhere that is going to lead to a shortcut. The probability that none are defective is going to be the probability that all of them are good. So that means the probability the first one's good times probably the second one is good times probably the third one's good. So the probability of being defective is 0.1. The probability of being good is going to be 0.9. So this time it's going to be 0.9 times 0.9 times 0.9 times 0.9. So if you're looking up at the whiteboard, that's going to be that top branch. So the first one's good, the second one's good, the third one's good, and the fourth one is good. And that is going to be a probability of about 66%. Part C, and this one's a little interesting. What is the probability that one of the 4 is defective? And by that I mean exactly one of the 4. Well, there's a few different ways that this could happen, because if one is defective, that means the other three are good. So it could be possible that the first one was defective and the other three were good. So you get 0.1 times 0.9 times 0.9 times 0.9. Or it could be that the first one was fine, but the second one was defective, and the third and fourth were okay. Or it could be that the first two were all right, the third one was defective, and the fourth one is okay. Or the first three were good, and the last one is bad. Now I think you can see that each of these is going to have a probability, each one of these branches, and if you look at the board you can probably figure out which branches they are. Each of these branches is going to have a probability of 0.1 times 0.93 times, or 0.1 times 0.9 to the third power. Since there are 4 of these branches, I'm just going to multiply that by 4. So each one of these branches would be 0.1 times 0.9 to the third power. Since there's 4 of these branches, 4 possible ways that this could happen, I'm just going to find what that is and multiply it by 4. And you should find your final answer is going to be something like 29%. And finally, what is the probability that at least one is defective? You probably have already figured this out, because if you look up at the board, you probably really don't want to find the probability of all those other 15 branches and add them together. The probability that at least one is defective is the complement of none being defective. So the easiest way to figure out the probability that at least one is defective is to do 1 minus the probability that none are defective, which we already did back in Part B. So 1 minus the probability that none are defective, which should give you something like 34%. Okay, pause the video here. Do your best on the last page. When you're completely done with that page, go ahead and play the video again and we can check our answers. Hopefully your answers look something like this. The probability that a student chosen is female is going to be 55 out of 100. The probability that a student is female and going to college is going to be 40 out of 100. The probability that a female student is going to college is going to be 40 out of the 55. So it's going to be 40 and the denominator has changed to 55. It's just at that one particular row. So it's a probability of or you can do it as the count of people who are female and going to college over just those that are female. Part D was, are being female and going to college independent events? So I did it this way. The probability of going to college, I'm comparing that to the probability of going to college given that you know someone is female, and it turns out that no, they are not the same number. You could also have done it this way. The probability that someone is female compared to the probability someone is female given that you know they're going to college. And you might say, well, I mean, yeah, 0.55 and 0.5 are not the same number. Clearly these are not the same. These two things are not independent. In this sample, at least in this group of people, of 100 people that I have, these two things are not independent. But you know, 0.5 and 0.55 are not actually that far apart. Can I make a conclusion about the population? Can I figure out if these two things are independent in the population? And to answer that question, we would be going back a few weeks and you would be doing a chi-square test for independence. That's when you're making an inference about the population. You say, okay, well, I mean, clearly it's not going to be independent as far as I know in this sample. But if I want to use these data to make an inference about the population, I'm doing a chi-square test for independence. I'm going to check and see what would my expected counts be if they really were independent, and compare that to what we actually got. And is it different enough to be statistically significant? But as far as we know, right now, these are not independent events. And finally, what is the probability of being male or going to college? It's going to be 85 out of 100. And there's 3 different ways you could have done it. At this point, probably quite a few of you guys are doing it this way. Probability of being male plus probability of going to college minus the probability of being male and going to college, that is, subtracting these people who just got double counted. Or you might have used the complement rule and did 1 minus the probability of being female and not going to college. Or you might have just added together those 3 subgroups in order to get your total probability. All right, and that's pretty much all we have for today. So, finish up with this. Go back and fill in anything that you didn't have time to do because you didn't pause when you were supposed to. After you've finished, I strongly suggest you do your homework. After you have finished, if you would like to, you can also get your test from your substitute because she will be letting you guys have those back after you have completely finished your notes. Actually, before you get that, before you go and stop the video, let's actually take this opportunity to talk really briefly about your guys' tests. So one of your free response problems looks something like this. And honestly, I think a lot of you got a little bit freaked out because of the fact that there was a lot of space under this question, describe the nature of the relationship. And that's really just because if you look on the next page, there's a whole bunch of stuff up here. And they wouldn't have been able to fit all of this stuff onto this page if they hadn't left it blank here. Like they wouldn't have been able to put all that here plus give you enough room to write. And that's, I think, why there was so much space on here. But all you really needed to do to get full credit on this question was to discuss direction, form, and strength. A lot of people had trouble with their adverbs. I had people saying it was strongly curved or strongly negative, which you don't really want to do. You want to make sure you address all three of those things, direction, form, and strength. For part B, interpret the value of r squared. I expected everyone to do fantastic on this, especially because if you look at the next question, it asks what proportion of the variation in electricity production is explained by its linear relationship with wind velocity, and I kind of figured that a lot of you guys would just kind of use that in order to answer your question for this one, interpreting the value of r squared. Most of what people missed on this one was the context, because it's the proportion of variation in the response variable that is explained by the relationship with the explanatory variable, or by the linear relationship with the explanatory variable, or by the linear regression line, something like that. However, a lot of people miss the context, because if you look at what the variables are here, these are the transformed data. So this is the natural log of the rate, and this is the natural log of the age. And a lot of people failed to put that these are the transformed data, that these are the natural logarithms of the impact rate and the age. That's why people missed part B. Part C, comment on the appropriateness of the linear regression for modeling the relationship. Well, they gave you a nice residual plot right here, and ladies and gentlemen, those of you that thought this was random scatter had better look again. All right, and on the back. So the last question you guys had looked like this. It was bound windmills. Part A, use a computer output above to determine the equation of the least squares regression line. Identify all variables using the equation. Most people did okay on this, putting the equation together. The people that messed up, it was mostly about the variables, so I'm not going to worry too much about that right now. We're going to keep on going. How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when it's 15 miles per hour? Most of you guys answered this by using your equation from part A, plugging in 25, plugging in 15, and finding the difference, which is totally fine. It's probably how I would have done it as well. Part C, what proportion of the variation in electricity production is explained by its linear relationship? Yeah, I certainly hope that no one had difficulty with this. Most people had difficulty with this. It wasn't because they couldn't find the number, but it was because they actually tried to interpret this and they interpreted it incorrectly, even though they gave you the interpretation in the question. So I'm not really sure why people decided they wanted to get creative and make things up that were not true. Last thing, is there statistically convincing evidence that electricity production is related to wind velocity? Well, statistically convincing evidence. Normally when you see that, it means do a test. With the exception of occasionally there will be a part where you have to come up with a confidence interval, and then after you do a confidence interval, they say, based on your interval, is there convincing evidence? And then that's the thing where you're basically seeing whether a particular value is inside your interval or is not inside your interval. However, there is no interval in this question. So yes, this is actually talking about a test. Is there statistically convincing evidence that electricity production is related to wind velocity? You will note, however, that they have actually done the work for you. They gave you the t-statistic and the p-value. So all you really had to do was the state and the conclude. So that means that you had to give hypotheses and, context and stuff, and you need to conclude in context. Since my p-value is greater than or less than my alpha, you reject or fail to reject, and there is or there is not statistically convincing evidence, and to do all that in context. So I think that's really all that I had to say for you guys. So please make sure you are ready. Next class is your last chance to ask questions before your test. Once you finish this video, please do go ahead and get your test back from the sub and go ahead and work on whatever you guys need to work on for your homework. I will see you next week.